morning, student. My name is Ernest Ntutuzin Kambule from Sibande Setu campus at Gert Sibande TVET College. Today I'll be presenting a lesson on Level 2 Electrical Principles and Practice, where I'll be talking about how to balance a load. Okay, I'll start with this thing it started from. We were having an alternator from the ESCOM side. An alternator will have two poles, a north pole and a south pole. And then an alternator, which is the rotating part, which is the rotor. So in this case, we will have the one with 3 slip rings. These 3 slip rings, that's where we will be having our 3 lines. Line 1, line 2, and line 3. We can also call them phases, where we have a red phase, a white phase, and a blue phase. Remember, this white phase can also be represented by a yellow phase. Okay, from this side, I won't touch because it's on another level. These parts of three phases coming from a slip ring, they go straight to a transformer, which is configured in delta. So our primary side of the transformer will be configured in delta. That's why we'll have our primary as delta. We can say, let's say, the alternator has given us 11 kV. Then these 3 lines, they go to delta. Then our secondary side will have a star point, which will be stepping down the voltage to, let's say, 415 volts. So you will still have 3 lines again. But now the only difference, you are now having 4 wires, because now this part, we call it a star point. So from a star point, that's where we got our neutral. Then from the neutral, now we are having a 3-phase 4-wire system, but we also need an earth wire. We are earthing the neutral for what? For faults. If there are faults, they should go through an earth. Then we have the feed wire, which is earth. That's how we got our 3-phase 4-wire system. So now, because we are having a transformer, which we said it's a 11 kV to 415 volts, we need to balance a load from this 415 volts for commercial use or domestic use. Okay, then we said from the secondary side of our transformer, we are having what? 5 lines now. That's why we got our 3-phase 4-wire system. These lines now are coming from the start point of the transformer. So we still have line 1, line 2, line 3, then neutral, and earth. So this line 1, it can be a red phase, white phase, blue phase, neutral, and earth. So now we need to balance a load. The reason for balancing a load is 1. Remember, our transformers are rated in kVA. So for instance, if we are given a 50 kVA transformer, we mustn't exceed that kVA, or else the transformer will explode. So we are balancing a load now. So by balancing a load, what do we mean? Each phase must carry the same load. No line must be pulling more voltage or wattage than the other one. So I'll make just an example. Let's say you are supposed to supply in your location. You will have 10 houses being supplied in one phase. Then you'll have another one supplied in the other phase, the other ones on the other phase, like this. They will take 10 houses from the red phase straight to the house. Then they take the neutral straight to the house. Then they also take earth. Then they don't repeat the same thing on the same phase. They must now go to the second phase, which is white phase. They tap it again, line 1. Then they take neutral and earth again. Then they do it again on the blue phase. On the blue phase, they tap again the red phase. This blue phase is a live wire, remember that. Then they take the neutral and earth. Okay, these are only for single phase loads. Then now your load is balanced. For example, I was saying this is for 10 houses from your street, 10 houses from my street, and 10 houses from the other street. So even if there's a fault, you will find that in this location, in this street, they don't have electricity. It is because of what? That other phase is dead or something went wrong. But the other two phases will be having electricity, but it will trip at some time because now the transformer is malfunctioning, is pulling more power on these two phases compared to the other one. So that's the reason why we are balancing a load. Then if we are balancing three-phase loads, you will find that like we are balancing for induction motors, which they require three phases. Then you take one line from your red phase, you connect it straight to your motor. You take another one from your white phase. You take another one from your blue phase. But then now you don't take neutral, you take earth only. Because now this motor can be either configured in two configurations. It's either configured in delta or in star. So if it is connected in star, it means that now the star point will serve as a neutral. But then if it's configured in delta, you don't need a neutral. So that's why you'll be only taking red phase, white phase, blue phase, and neutral, then and earth, not neutral. From there, your phases are balanced. All your loads are loads are balanced through these phases. And then for another example, if you can check at home, you have appliances which they have different wattages. For instance, your kettle, your geysers, your stove. If you can calculate all those wattages, you remember when we were doing calculations, we have a formula like this, P is equals to VI. Then let's say you manipulate this formula, you make I subject of the formula, I is equals to P over V. You will find that when you add all these currents of your appliances, they won't exceed the given amperage, which is 63 amp for your household. So as soon as you exceed that 63 amp, your leakage will trip, meaning now you are requiring more power than what you are being given. So you can try it when you're at home to balance using this formula that I'm giving you. You take the wattage for your kettle, you add, for example, you can say it takes 300 watts, then your iron, it takes, let's say 600 watts, then your bulbs, they take 100 watts. Then you add the totals will give you 1,000. Then for power, you are consuming 1,000 watts. This is just an example. Then you manipulate the formula. You say I is equals to P over V. And then you put your 1,000 watts, you divide by the given voltage, which is being single phase. It will be 230 volts. I is equals to P over V. This is power, this is your voltage. Then you divide 1,000 by 230. Then you will get 4,347 amperes. Then now you see that this amperage doesn't exceed the 63 amp that you are given as a consumer. So that's why we balance a load. Then during your exam, this is what they do, and they don't include this part. I was just showing you an example. They will give you different types of loads. They will ask it like this. They will give you different types of load, then they will require you to balance them. For example, they will give you 3 toasters of 300 watts. So it will be 3 times 300 watts. And then let's say they give you 4 geysers of 400 watts. I'm just making an example. Then they give you, again, what? They give you 5 heaters, maybe, of 300 watts. So what you will be requested to do is to add all these wattages. You will say 3 times 300, you get your 900 watts. You say 4 times 400, you get what? Your 1,600 watts. You say 5 times 300 watts, you get your what? 1,500 watts. And then now, since you have these totals, you want to balance them in a 3-phase system. You add these total wattages. You will say 900 plus 1,600 plus 1,500. and then you get 4,000 watts. Okay, but then now you want to balance all this load in a three-phase system. You will divide this 4,000 watt by 3. This 3 will represent your what? Your 3 phases. So, okay, as I've drawn here, I'll only put the values on what is representing what's there. So when you say 4,000 divided by 3, you will get what? 133,33 watts. So meaning now, each and every phase here, from red, white, blue, they must each carry 133,33 watts. So that's why you go back again here. You remember what you did firstly. So you will check, you are having what? You are having 3 times what? 300 watts. Meaning, since they are 3, in each phase you will connect one heater. It's a single phase heater. You will say red, white, red, neutral, and add on for one heater. Then for the other one again, you come, you put, meaning you'll have a long diagram if you're having this long information. So you'll put white phase for one heater, and then you put neutral and add. For the other heater again, you put it on another load, and then you put your neutral and add. Again, you do it. Now remember, now you are having 4 of this other type of load. Then you say 1 for each phase, or you can put 2 for each phase, since here they are saying 4. You can put 2 on each phase and 2 on the other one. Then you come again on this one. Since there are 5, you can put 1, 1, 1, and then you put 2 on the other one where you didn't put 2, since on the first one you put 2, 2. Okay, this is all about it on load balancing. You are just requested to balance your load through three-phase 4-wire system. From there you are done. You are protecting your transformers, on which this is the lesson I'm going to present after this one. Okay, students, for now we'll be focusing again on transformers. But you know, since this is level 2, we'll be only dealing with single-phase transformers with no load, which is called IDL Transformers. So we'll start with a basic principle or a construction of a transformer. Your transformer will have a transformer core, and then it will have the primary winding and the secondary winding. That's how your transformer will be. And then in these transformers, what you will notice, you will have a step-up or a step-down transformer. What will tell are the number of turns on the primary side or on the secondary side. If you have more on the primary side than the secondary side, then you must know that this is your step-down transformer, vice versa. So we've said this is the primary winding, this is the secondary winding, this is the transformer core. So you have 2 types of core where they can laminate, where they can put your windings. The one that I've just drawn first, it's a hollow core. Then you also have a shell core. A shell core looks like this. It's like an alphabet E with a lid of an I. So they put all these things laminated together, and then they form a transformer core. From there they put windings on this core. But normally this one is used in 3-phase transformers. As you see, this E, you can put the first windings, the second ones, and the third one for 3-phase transformer. And remember, we said to form a three-phase transformer, you must have 3 single phases connected together. It's either you connect them in star or in delta, depending on what you want to achieve. Then you will use any configuration. So we said we will be using a transformer with no losses, which is an ideal transformer. Then we have 2 types of core, a shell core and a hollow core. So when you come to calculations on a transformer with no losses, which is an ideal transformer, we'll be using calculations like this. V1 over V2. It's equals to N1 over N2. It's equals to I2 over I1. This V1 will be your primary voltage, V2 your secondary voltage, N1 the number of turns on the primary side, then N2 the number of turns on the secondary side. Then I2, it will be your current produced on the secondary side, I1, the current produced on the primary side. So when you are given a data to calculate, they will give you only 3 unknowns to calculate 1. And then you will make the subject of the formula of the unknown that is not given on the data, but we will make one example of it. So we said it's a transformer with no losses, but remember, it doesn't mean that a transformer doesn't have losses. Transformer does have losses. We have copper losses and iron losses. Those are 2 types of losses that you are having in a transformer, but we will deal with that at a later stage. Then you also have what? Well, we said we have losses. Then we also have types of cooling in a transformer. A transformer, when it operates, remember on the previous lessons, you were having a formula whereby you calculate the resistivity of a material, which was like this. So there were factors which affect the resistance of a material. You also had another one where you were calculating the heat generated by the circuit, which was saying Q is equals to I squared RT. So these formulas, when you combine them together, they are the effects that happen in a transformer. That's when it starts to have all these losses, the copper and the iron. So heat is being generated when there are these losses. So a transformer will need to be cooled down. So we have 2 types of cooling. We have oil cooling and oil cooling. Under air cooling, you'll find that a transformer where it is mounted, they put fans outside it. These fans, they blow air through the transformer. And then on the oil cooling, you'll find that the windings of a transformer, let's say for this one, they take that core with its windings, and then they they deposit it inside the corrugated tank of a transformer. Then they seal it, they put a corrugated tank. That's how it's being cooled. So the oil will circulate inside. Then you ask yourself, why there is no short circuit? Because this oil is a liquid. The reason for that, the oil also serves as an insulator, so it doesn't conduct electricity at all. So it's having 2 functions. It serves as an insulator, it also cools down the temperature of the transformer. So then let's come again to calculations. You will find that now we are given a data. They say, calculate the number of turns of a transformer. Let's say you are given 400 volts on the primary, and then we'll say, let's say it's V1. Then you are given 200 volts on the secondary. This is your V2. Then they say the number of turns on the primary side is 30. The number of turns, they don't have an SI unit. So they say they want you to calculate on the secondary side. They want N2. You'll go back to your formula, then don't cram or memorize this formula. It will be given during exam on your formula sheet. So you will manipulate this formula, checking on what do you have. You will manipulate the formula and make N2 the subject of the formula. How do we do that? You will say N2, it's equals to V2 N1 divided by V1. Then you substitute all the data that you have. So we said we have what? V2 as what? As 200. Then here, because it's a product, you multiply by the number of turns, which is 30. Then you divide by the value of V1, which is 400. From there, you take your calculator, you calculate it's 200 multiplied by 30, which will give you 6,000. Then you divide it by 400. Then 6,000 divided by 400, it gives you 15. So it means when you are having this type of a transformer, you're having 30 turns on the primary side. On the secondary side, you'll be having 15 turns. They can also require you to say, can you give us a ratio of this transformer? So by saying the ratio, they are referring to the number of turns. So let's talk about the same transformer. The primary voltage is 400 volts, the secondary voltage is 200 volts, and this transformer is a step down. As you see, the primary is greater than the secondary. So what you do, you're having two voltages, you want a ratio. What you do, you will say V1 divided by V2, it's equals to, you put that 400 volts divided by 200 volts. So you will say 400 divided by 200, which will give you 2. So you don't only write 2 because you want a ratio. So you will say 2 is to 1. Then this is the ratio. Then this ratio, what does it represent? It represents that this 2 is N1 and this 1 is N2. So even if you can substitute again these values, saying these are your number of turns, you will get all these values that you want here. Let's say you want V2, we're having N1 and N2. You can manipulate the formula, you will get this answer. So it goes like that on transformer calculations. We also have another transformer, which we didn't mention here, which is called an auto transformer. An auto transformer, it has one winding. So for a schematic diagram, it will be something like this. Then let's say this is the supply, and then this is your load. So an auto transformer, how does it operate? It will have tappings here on the windings. Remember, it's only having one winding. For an example of it, I can say your stove element. It has 6 knobs there. The 5-heat stove or a 3-heat stove. So by tappings, I can refer to that switch. When you put your stove on position 1, it's not warm than when it's in position 6. So in these tappings, what they do, you'll find that here it's 100%. It means that now the transformer, it will be operating at maximum windings. Here it can be 50%. Here we can say 25%. So with these percentages, depending on how many windings do you want, or how big is your load, what do you want to supply, then you'll do calculations as we did. After balancing your load, and then you choose the correct tapping. For instance, you want 50%, then you don't want all the windings, then you put it on 50% as that switch. It has a switch, that's why it's called a tapping. So you tap it to 50% or you tap it to maximum, depending on what you supply. Okay, students, to summarize what we have done from load balancing to transformers, we remember for load balancing, we said we must have 3-phase 4-wire system, then you have to balance your load. By doing what? By making sure that each and every line or phase is taking equal. And then we said you must also do the calculations to make sure that you don't exceed the transformer rating, because we are balancing it so that the transformer cannot explode. We went again to transformers. We do all the calculations. We said you are having an IDL transformer, which is a transformer with no losses, but that didn't mean a transformer will have no losses. We said we are having 2 losses, which is iron and copper losses, but for now on your level you'll be dealing with ideal transformer. We said we also have an auto transformer. We mentioned that we have 2 types of cores, which is hollow core and shell core. The other one is used for 3-phase in most cases. And then we said we have what again? An auto transformer, a transformer with tappings. It only have one winding. You choose your windings when you are balancing your load. You will see that, okay, I need maximum, then you put it at 100%, then that's it. So we'll see each other on the next lesson. Goodbye, students.